Welcome to Let's Leetcode. Hi guys. Today our lucky number is 693. Binary number with alternating bits. Question is kind of straightforward. So given a positive integer, check whether it has alternating bits. Which means if two adjacent bits will always have different values. So if you look at the examples given, n is equal to 5. The input is 5. The representation of 5 in binary is 101. 101 alternates, hence why the output is true. For the second example, 7 is given, output is false. The reason is representation of 7 is 111, and 111 doesn't alternate. And then if we look at the fifth example, n is equals to 3. The binary representation of 3 is 11, and 11 doesn't alternate, hence why the output is false. The constraint is that n will always be in the range of 1 up to 2 raised to the power 31 minus 1. The obvious solution to this problem would be to iterate through the bits and then compare adjacent bits to check for equality. If they are equal, then it means they are not alternating. You return false. But before I illustrate the algorithm, first off, let's recall that to convert a number from base 10 to base 2, these are the steps you have to take. So for example, converting 11 to base 2 would be 11 divided by 2 would be 5, remainder 1. 5 divided by 2 would be 2, remainder 1. 2 divided by 2 will be 1, remainder 0. 1 divided by 2 will be 0, remainder 1. And then you count your remainders from bottom to top. And then you have 1, 0, 1, 1. And that's how we got to this number. And now to continue with my approach, you start counting from the second element, and then you iterate through like all the bits. So you start from this element, and then you check if the previous element is equal to the current element. If it's equal to the current element, you return false, because it means that the bits are not alternating. Otherwise, you move to the next element and you repeat the process. You check the previous element and then you move to the last element and you check again. So now we need to get the bits from the decimal integer n. And to do that in Java, we check the docs. We can use to binary string on an integer to give us the value in base 2. So let's quickly do that, and gives us a string value of decimal integer. And then we can check starting from the second item, because it's 0 indexed. We can do and then just iterate through to the end of the string. And then at every point we have to check if the current value is equal to the previous value. So we can do that and say value at character the previous character, if it's equal to the current index, if it's equal to the character at the current index, then we return a false, because then it means the bits are not alternating. Otherwise, keep going, and at the end of the loop, return true. So let's test and see. Nice. Nice. The second approach would be to divide by 2, which is kind of similar to the first approach. So the whole idea is, if you have, say, 11 and you divide by 2, you have 5, remember 1, and if you represent 5 in binary, you have 1, 0, 1. The concept is always to check if this value equal to this value, and we can keep breaking it down by doing this just to further illustrate. This gives us 2, remember 1. 2 in binary is, and we can see that this is this plus this. Again, this and this, if it's equal, we break out. If it's not equal, we continue till we can't divide the number anymore. Okay, so we need a number to hold the last bit. So last bit is the remainder, basically, like I showed in the illustration. So we have the remainder, and then we need to actually divide the number by 2, and then we do a while loop to ensure that the number is greater than 0, which means that we can still divide the number. And then we check if the last bit is equal to, then we check if the last bit is equal to the end bit of the current number. If it's equal, it means it's not alternating, and then we return a false. Otherwise, we keep going in the loop, and we have to update the last bit to be the bit at the end of the number, and also update the number itself. And it does this repeatedly, and if it doesn't find 2 adjacent bits to be equal, it completes the while loop, and then it returns a true. And so let's test this. Nice. Approach is similar to the previous one, but the difference is we'll be using bitwise operators instead. So instead of dividing by 2, to get the last bit, we can just do a bitwise AND with a number. So if, for example, if we have 5 in decimal, bitwise AND with 1 will give us 1. 11 in binary is this. Bitwise AND with 1 will give us 1. 4 in binary is 100. Bitwise and with 4 will give us 0. And so we can get our last bit with the bitwise AND. And then to get the remainder, instead of actually dividing the number, we can use the right shift operator. So right shift operator looks like this, and it's basically shifting a bit by one place off from the right. So 5 in binary right shift operator by one place would give us 1 and 0, because we're basically throwing this guy away. If we do 411, right shift operator by 1 would give us 101, because we would make do, we'll throw away this guy. And so with this, we can just implement the same algorithm we implemented in the previous example. We always check the last bit with the end of the current number. And the same with this, we check the last bit with the end. We just keep repeating the process until we can't go further with the operations on the numbers. To get the last bit, we need to do a bitwise AND with 1. And to get the value after dividing by 2, we need to do right shift by 1. And we repeat the process for this one. And to get the last bit, we need to do AND here. And yeah, we need to do this. And then we'll try again. And yes.